All right, everyone, welcome to our first chemistry virtual lesson. So first things first, welcome back from spring break. I hope you and your families had a little bit of time to maybe rest and kind of spend time together during quarantine. At least you weren't bombarded with schoolwork for a week, but now we're back, and so some more schoolwork for you. As you know from your other classes, kind of teaching like this virtually is a little bit weird for us teachers. So just kind of bear with us as we get the hang of it. The first lesson I thought we'd tackle today in chemistry is on balancing chemical equations, right? So this is technically lesson 2 in our 11th grade Google Classroom. And lesson 1 had you kind of watching a brain pop video and also looking at a virtual lab that talked about how these chemical equations are put together and how we can tie a little bit of math into our chemistry so that we are able to um, take a reactant, and as long as we know the chemical equation, we can determine using our math skills exactly how much product is going to be made. So if I tell you, hey, this is how you make hydrogen gas and oxygen gas into H2O water that you can drink, and I tell you, hey, you can start with 2 grams of hydrogen gas, you're going to be able to tell me exactly how much water we'd be able to make at the end of your reaction. And so this is super useful, especially if you're trying to go into not just being a scientist and being a chemist, but even being a pharmacist, being a nurse, being a doctor. You have to know exactly how much of certain chemicals your patients might need, or if you're a mechanic or an archaeologist or any other kind of field that uses chemicals and substances, then you're going to definitely want to know a little bit of the math that goes into chemistry. Okay. And so I thought that this would be a great place to start because some folks were like, I got it. Lesson 1, I saw the brain pop video. I understood exactly how the virtual lab worked. Some people are kind of more on the fence, and some people are saying, hey, I just don't understand what's going on at all. So the key for this kind of new topic in chemistry is to look at it from a bunch of different ways, right? And so I wish that we were back in the classroom with models and mini labs where I could show you exactly how things are put together. But using kind of a virtual, setup, and I've got some models, I think that I can still show you exactly how things are going to work. And so stay tuned because we're going to try to get creative with it and try to get some good learning opportunities here. Okay, so the first thing you'll need, if you look at my screen here, right, I shared my screen with everybody. The first thing you're going to need is this handout. And so this kind of lays out nicely a lot of the ideas that we looked at in lesson 1, especially through that brain pop video and through the virtual lab, kind of re-emphasizing all the main points so that you have them all in one note catcher. If you don't have access to a printer, that's totally fine. Just take a look at this this note catcher outline. It's in the Google Classroom kind of assignment, and grab yourself a blank sheet of paper and then kind of try to organize it a little bit like the note catcher so that you have all your notes in one place. Okay, you don't need to turn in these notes, but you're going to want them for the homework assignment and for all the assignments going forward. Right, so it looks just like this: balancing chemical reactions. And so we're going to get started with a PowerPoint. This video is going to be maybe 20 minutes long, and it'll be kind of going through the entire PowerPoint, and you're going to use this note catcher to fill in some notes. Okay, let's get started. So here we go. Now you're not going to see kind of the video of me as we go through the slideshow because PowerPoint doesn't work that way, but I'm still here. So let's do it. All right. Very first thing in our slideshow. I love to put in some memes at the beginning, right? So when you start doing chemistry and you learn how to balance equations, right? So you got this balanced chemical equation right here in Thanos' hand, right? And it's perfectly balanced as everything should be. And then one more here, you got Rick and Morty. Chemistry teacher introduces balancing equations. Well, that just sounds like math with extra steps, right? Some of you were writing in the comments to either me or Mr. Jones. Why does our chemistry have math in it now? Ah, what's going on? Don't stress out. It's not complex algebra like like you might be doing in Mr. Jones's class. Very simple math, just got to get the hang of it. All right, so let's get started here. So you're using your note catcher to take some notes. All right, some goals for our lesson. So first, you're going to describe the law of conservation of mass. A lot of you already kind of have it in your heads, but the more you work with it and the more you kind of use it, the more it'll kind of be ingrained in your memory, right? And you want to explain how this relates to a balanced chemical equation. So when we say law of, we're talking about a law of nature, right? This is something that we can prove over and over and over again with any given experiment, right? So the law of conservation of mass. And then the next goal is going to be, we want to balance some chemical equations. We actually want to put pencil to paper, and we want to actually be able to fix some broken equations. All right, so let's get started. With your note catcher, looking at chemical reactions. So realize that when we talk about chemical equations, we're talking about kind of the symbols and the letters and the numbers that make up and represent a chemical reaction, right? So whenever you see anything bubbling in a test tube or you see something exploding, there's a chemical reaction that describes what's going on, right? And realize that here in this chemical equation, we are breaking bonds and then rearranging them, rearranging the atoms to make new bonds. So take a look at this. You can picture the atoms to be these different kind of shapes, right? So you might have a hydrogen represented by a yellow square or a carbon represented by a purple circle or something. But realize that we're just taking, think of them like Lego pieces. We're just taking atoms, we're sticking them to atoms with bonds. And then when we do a reaction, we just break those bonds and we reshuffle those atoms around to make new compounds, new molecules, right? So you think of it like a Lego, maybe like a Lego car, right? It's made of a bunch of different pieces. And then if you want to make a new shape or a new thing, you just take those same exact Lego pieces and you make that into like a house, right? Use the same pieces, rearrange them. We do the same thing with atoms and chemical equations and chemical reactions, I should say. So if you look at this diagram down here, right, the different colored shapes are now taken apart and put together with other shapes. That's exactly the same thing happening with atoms. All right, let's keep going. The other thing about chemical reactions is that mass is always conserved. It always stays the same here, right? So if we look, we realize that the law of conservation of mass tells us that the mass of the reactants, what we start with, always equals what we end with. We're not creating or destroying anything. Okay, no matter is being created or destroyed. What you start with is what you end with. Okay. So here's the definition here. So you're looking at your note catcher here. Top of the page, you should already have a chemical equation definition, what happens in a chemical reaction, and now we're trying to describe the law of conservation of mass, right? So if you look where it says mass is conserved, right below it, it says according to the law of conservation of mass, and then we want to jot in here, okay, the number of atoms of each type is the same on both sides of the equation, right? Think about that for a second, right? The number of atoms of each element is the same on both sides of the equation. So if I got 4 carbons on the left, I gotta have 4 carbons on the right. If I have 2 oxygens on the left, I gotta have 2 on the right, right? So the number of each type of element is the same. This confuses students sometimes, so you wanna make sure that this is really clear. And then you wanna make sure to maybe jot down or draw in this image, or if you wanna represent it in maybe like the equation for sandwiches from our virtual lab, right? 2 pieces of bread plus 1 piece of cheese equals 1 sandwich. You could do a drawing like that. But here in the slideshow, right, we're using different colors, squares and circles to represent, oh, okay, right? Taking atoms apart, putting them together in different orders. Okay, and feel free to pause and rewind or slow me down or speed me up as much as you need. Okay. So then we move on to how to write a correct equation that actually complies with this law of nature, right? If the mass has to be the same on the left as on the right, how do I write an equation and make sure that it follows that law of nature? So let's take a look. Okay, so if you have an equation that's off, the reactants don't quite equal the products. You don't, maybe you have 3 carbons on the left and 4 carbons on the right. Something's off there if you're looking at that equation. We're going to look at some examples in a second, right? But if something's off in your chemical equation, you have to fix it. You have to adjust it so that you make it comply with that law of conservation of mass, right? So this checkpoint here on the slideshow is telling us, okay, look, the amount of reactants used and products form, right? Remember, the reactants is what you start with. They get used up in the reaction and then they form these product molecules. You have to make sure to fix both sides of your equation so that you have, again, the same type of each element. I'm sorry, the same number of atoms of each element on both sides of your equation, right? That's crucial. So let's take a look here. This process is called balancing the equation. Okay. So this, you should have this in your note catcher, right? This process is called balancing the equation. All right, let's take a look here. So balancing an equation, the only way to balance these equations is to insert coefficients, right? And so if you're not clear on maybe what a coefficient is or what a subscript is when we say these words, I'll show you on the next slide here exactly what I mean by that. Let's take a look. You want to insert coefficients when you're balancing an equation. So next slide here, let's see. Maybe I can make my, okay. So if you look at my mouse here, right, you've got a chemical equation here, for example, right? We talked about this right at the beginning of our lesson, making water. Okay, so we got we got H2 plus O2 is going to yield, right? This arrow, just like in math, when you see an equal sign, you know that's saying, okay, 2 plus 2 equals 4. In chemistry, we use this arrow and we want to make sure that we say it right. So when we see an arrow in chemistry, that means yields, right? So H2 plus O2 yields H2O is how you would say this reaction. If someone asks you, hey, how do I say this? It's written down, but how do I say it? Right, H2 plus O2 yields H2O. Okay, so then we take a look here. Okay, we've got H2, right, on the left. 2 hydrogens bonded together into a molecule. Then we got O2, oxygen, same deal, bonded together in a molecule, right? So these are represented by, here you got the H2 represented by the 2 yellow circles, and then the O2 represented by the 2 red circles, right? These are bonded together with that little line, that's a bond. And then the arrow here tells us that these 2 are being reassembled into a new molecule. So then you got H2O, which of course, you know, is oxygen and 2 hydrogens here, boom, bonded together nicely. So here we realize that, okay, I got 2 hydrogens on the left, 2 yellow circles on the left, and 2 yellow circles on the right. Perfectly good, all right. And then I got 2 red circles, 2 oxygens on the left, and only 1 red circle, only 1 oxygen here in my H2O on the right. So something's wrong, right? This equation is all messed up because my reactants don't equal my products. So let's try to fix it, right? There's not enough oxygens. A lot of you did this nicely on the Brain Pop Part 1. What was that? The Google Doc assignment, right? A lot of you did this nicely. You realized, oh, okay, I'm missing something on one side of my equation. So now let's talk about how to fix it. Okay, so you should have, this is in the example section. Right, we're balancing chemical equations, and then you got the example in your note catcher. Okay, good. So let's keep going. So like we said before, we want to insert coefficients to balance these equations, right? So right now, the way things stand right now, you've got coefficients of 1, right? Whenever you don't see any number in a chemical equation, whenever you just don't see a number, right, assume that it's 1. So in the last slide, we saw that these guys didn't have a number in front of them. We assume that to mean, okay, these have a coefficient of 1. Now, when we look at this, we realize that we can change the coefficients. We can change these big numbers hanging out in front of each molecule, because what those coefficients do is that they'll tell us, oh, this is how many of each molecule I have in my reaction, right? So if I've got 1 H2, that means I have 1 molecule of this H2 guy hanging out. And then if I have one O2, that means I've got one molecule of this O2, right? And then one H2O means I've got one H2O molecule, right? So you don't want to get coefficients, the big numbers in front on the left, confused with subscripts, which are the little numbers to the right of the element, right? Because the little numbers, the subscripts tell you I've got two hydrogens inside of this molecule, whereas this big number tells me I've got one molecule overall of water, right? Okay, so we can change the coefficients, but we can't change the subscripts. So let's try to fix this reaction by changing some of the coefficients here. Let's take a look. And remember, our goal is always to get the same number of each atom on each side of the equation. Okay, so let's take a look here. Now, how should we actually approach solving this, right? There's a few options at our disposal, right? So this becomes kind of like a math problem now, okay? We need to figure out what makes this equation balance out. We have a few options. One of our options is you could do some pretty complex algebra, right? You could take an equation like this and you could say, okay, the coefficient in front of each of these molecules is a variable A, B, C, D, and then you could do some funky algebra stuff, and you know, we could go on and on. This could be a whole year class just figuring out how to do this, but thankfully, no, this is not the way we're going to solve these at all. So sorry, Mr. Jones, we're not going to use complex algebra at all. What we're going to do instead is we're going to do trial and error. So what I'm going to do first, if I'm looking at this reaction, is I'm going to actually change my subscript. I'm going to raise my subscript up by 1 for water, right? So I'm going to make that subscript into 2 and realize what happens. All of a sudden, my number of molecules of water becomes 2. And so then I can just count up my oxygens. Oh, I've got, okay, 1, 2 on the left, and I've got 1, 2 oxygens on the right. The oxygens are good, but now look, I made a problem here with my hydrogens. I've got 1, 2, 3, 4 hydrogens on the right, and I've got 2 hydrogens on the left. So not good yet, right? So we fixed that oxygen issue, but we just made a hydrogen issue here. Okay, so we gotta also keep working at this and keep trying to fix this. So if I add another H2 molecule, all of a sudden, I realize that I need 2 H2 molecules, right? 2 sets of these hydrogens bonded together with 1 oxygen molecule. And then I know that I have enough of each of the reactants to make 2 water molecules, right? And realize that these bonds here are breaking in a chemical reaction. So these 2 oxygens aren't connected anymore. Once they become these water molecules, these 2 oxygens break up, and then these hydrogens break up, and then they make their new connections to make water molecules, right? So now the equation's balanced because we got the same number of hydrogens on the left as on the right, and we got the same number of oxygens on the left as on the right. So everything's good. We nailed it. This is perfectly done, right? So this is how you want to go about balancing these equations. Trial and error. Change your coefficient until you fix the number of each type of atom for a given one element, right? We started by fixing the oxygens. And then if you make another problem with another type of element, another element like we did with hydrogen, then you go back and then you fix the hydrogen, right? So start by fixing one element and then move on to fixing the next element so that your numbers match up. And I'm going to show you exactly how to do that on the first 2 homework problems at least. All right, so want to make sure we keep in mind, okay, coefficient times the subscript gives me the total number of atoms. Okay, so this is kind of a little bit of distributive property, right? So if you remember that from maybe algebra 1 or even earlier than that, realize that just like in math equations, right? If this was 2x squared, no, that's a bad example, sorry. If we look at this guy here, this coefficient, we got 2H2, okay? If I asked you, hey, how many hydrogens do I have on the left side of my equation? You would say, how could I tell? Well, so each molecule has 2 hydrogens, right, bonded together, right, the 2 yellow circles. And then if I have two of those molecules, all of a sudden I've got 2 times 2, I've got 4 hydrogen atoms. And so a little bit of quick multiplication, coefficient times subscript will tell me how many hydrogens I'm dealing with on the left. And then I can flip over to oxygen. I can say, okay, there's a 1 here, right? If there's no number, assume it's 1. There's a 1 times 2 for oxygen. So all of a sudden, I know I've got 2 oxygen atoms. And the same thing on the right side, right? Don't be discouraged or scared by these molecules that have more than one element, right? Like water. Take a look. If I look at the coefficient in front of water, I realize that I just do 2 times the 2 in front of the hydrogen, right? Just for hydrogen, focus on one element at a time. 2 times 2 here gives me 4 hydrogens. And then what I can do, and this is crucial, right? Students forget this sometimes. This coefficient in front of the H2O also applies to the oxygen. So this oxygen here, right, in H2O, it's got the 1 coefficient in front of it, right? It doesn't have anything in front of it. So we assume that that's 1 here. Oop. There we go. So we assume that that's 1 here. And we can just do 2 times 1, and then I know that I've got 2 oxygen atoms overall. Right? And we can double check our math by redrawing this little diagram, and we realize that, okay, 2 times the 2 in front of the H gives me 1, 2, 3, 4 hydrogens, and then 2 times the 1 in front of the oxygen gives me 1, 2 oxygens. Okay, so now we're making math work for us. All right, so let's do it. Realize that these represent ratios. These coefficients represent ratios. So I know that for every 2 molecules of H2, I'm going to need 1 molecule of O2. Just like if you think back to the virtual lab, right? You need 2 slices of bread and 1 slice of cheese to make a sandwich, right? You might need 2 graham crackers, 1 piece of chocolate, and 1 marshmallow to make a s'more, right? So if you think about them in terms of recipes, you think about like, okay, so what's my favorite recipe and how much of each ingredient do I need to make one of my recipe? That's exactly how chemical equations work, right? So I need 2 molecules of this H2 and 1 molecule of O2 to make 2 molecules of H2. It's the same exact logic as saying I need 2 slices of bread and 1 slice of cheese to make 1 sandwich or 2 sandwiches or however many, okay? You can think about them like ingredients. They work in ratios, right? So we have to kind of think back to not just kind of basic algebra, but also remembering how to work with ratios and what to do with them, right? Because they're going to be very important, okay? And then so realize here that these ratios, right, between these molecules are given to us by the balanced chemical equation. And then this is getting a little ahead of the game, but look, I can actually convert just by knowing the ratio of the chemical equation. I can actually convert this into how many grams of hydrogen gas or oxygen gas, H2O2, how many grams, how much actual mass of these gases I would need to make then an actual amount of water, right? And this is getting ahead of the game. This is going to come up in lesson 4 and 5, I believe. But realize that if we do the math and we convert these to grams, right, a unit of mass, then the mass of the reactants is going to add up to the mass of the products, right? So if we run through this math that you don't have to worry about just yet, but realize that we'll get 36 grams of reactants is going to equal 36 grams of products, right? So if I told you, hey, we only have 2 grams of reactants, and I asked you how many grams of product can we make, you would say, oh, we can only make 2 grams, right? Because the masses have to be equal on both sides. That's law of conservation of mass, right? You don't want to forget that. Okay, so now we are on the back of our note catcher here. And so we want to take a look at some things that you can't do. Okay, so here are some no's. Never do these. Okay, You can't change those subscripts. Please don't drive me crazy and try to change subscripts in your chemical equations, right? Realize that H2, this guy here, right? Those two hydrogens in nature exist together, right? You don't see hydrogens just running around solo. The same thing with oxygens, right? In nature, these exist as gas. These are called diatomic gases. And so these guys want to be together, bonded, right? You can't just say, oh, it's easier for me to say this is O3, and then, kind of balance your equation from there. No. You have to work with the subscripts, the little numbers that you're given, right? So then this kind of becomes a little bit like a math puzzle, right? So if you like, I don't know, Sudoku or something like that, then this is right up your alley, right? And so I kind of spoiled it, right? In class, I'd have you discuss with your partner, why doesn't this work? But realize that you just can't change these subscripts because you, a lot of times the way that the elements are put together in a compound is kind of the way they are in nature. So you don't want to change those subscripts. You can only change the big number of coefficients. So that's a big, big don't do. All right, so realize that H2O, right, is water. You can drink it, but H2O2 is a completely different molecule, right? Definitely don't want to drink hydrogen peroxide. Don't want to drink bleach. Please don't do that. These are completely different molecules, right? So you can't change those subscripts. All right. Now, another big thing is the coefficients have to go at the beginning of the chemical formula, right? If I'm writing H2O and I want to say that I have two H2O molecules, this coefficient has to go in the front out here. You can't just kind of shove it in the middle of a chemical formula because this doesn't really mean anything, right? You have to keep the molecules intact, right? So if you look at this molecule, for example, I would take a coefficient and put it in front here, never kind of in the middle, right? So you don't want to do that. Okay. And so one last thing before we actually do a few examples here, right? This is kind of another kind of throwback to some of your earlier math classes, right? So we want to talk about simplest whole number ratios, right? So if you take a look at an equation like this, same one we've been working with, right? And you might be tempted to say, okay, this one's good. Look, check it out. This one's good because I've got, look, 4 times 2, I've got 8 hydrogens on the left. And then over here, 4 times 2, I've got 8 hydrogens on the right. Okay, the hydrogens are good. And then you might say, okay, look, I've got 2 times 2, 4 oxygens on the left. And then 4 times 1, I've got 4 oxygens on the right. So, okay, this must be good. I'm done, right? But your answer would actually be completely wrong. You'd be 100% wrong because you didn't do a crucial step. You didn't reduce this to the lowest common factor, right? The simplest whole number ratio is the correct one. Realize that the 4, the 2, and the 4 here, the coefficients, can all be divided by 2. And so you have to go that extra step and make sure that your coefficients, if they have a least common factor, that they're divided by that factor, right? So this becomes 2 once I divide it by 2. This becomes 1 when I divide it by 2, and this becomes 2. So this is my correct answer down here. The coefficient should be 2, 1, and 2, right? That's the ratio I'm looking for. All right. So normally I'd ask if there's any questions or if I can clarify anything, but I can't see any of you, so let's just go right into balancing some equations.